All right, I think we can get started. It's basically 9:30. All right, so next couple classes we're going to be focused on alcohols. As a quick reminder, again, it's still feeling pretty brutal in here. So if you're not feeling well, this is not a joke. We've been told that you can go cool down in the dean's office. So I welcome you to go ahead and go to the dean's office to cool down if you need to. I will also sort of point out that I am videotaping these lectures, so if you're not feeling well, the actual more realistic thing you can do is, again, I won't be insulted if you have to get out of here. This is, it's in my opinion, truly unacceptable. Try to deal with it. All right, so today we're going to deal with alcohols. We kind of touched on them a little bit last class, and we will sort of be following up on these. And again, what I've sort of said in the past, and I'll reiterate because it's worth saying, is that everything that I'm going to try to do today and moving forward is going to be based on trying to tie all these reactions that we're going to go through to reactions you've seen in the past. And again, it's not going to work for everything, but it's going to work for a large enough portion of the reactions that I think we will be able to be okay. And so this is a bit of a sort of a restatement here. But, when we're talking about alcohols, in general, what we're referring to when we're talking about alcohols is molecules where you have a carbon on, right, an OH that's connected directly to a carbon. And so the simplest example of an alcohol would be this molecule here, which would be methanol, right? And we will often discuss alcohols as being, aside from methanol, we'll often discuss primary, secondary, and tertiary alcohols because of the sort of relative reactivity of these compounds. So, a secondary alcohol, as you might imagine, primary alcohol, right? We don't know what's going to be over there, but the point is that this would be a primary alcohol, right? Where the sort of carbon-oxygen, carbon-OH bond, right, is connected to a carbon. I don't want to confuse people there. But where that alcohol or that OH is connected to a carbon that's attached to two protons in addition to another carbon. Likewise, if we follow up on this pattern, a secondary alcohol would be one, right, where it's attached to two carbons, and then sort of carrying on, a tertiary alcohol would be one where it's bonded to three carbons. And what's important that I haven't really denoted here that's sort of worth mentioning at this point is, that could be anything, I'm just showing, I don't mean to say protons. Just the point is that they're carbons that are sort of connected to this. And so this one will be the tertiary carbon. Right, and I want to make sort of 2 points. This would be a tertiary alcohol, which is in line with what we've seen, right? We've seen this in the past with carbocations, right? You have a methyl carbocation, and you have a primary carbocation, you have a secondary carbocation, you have a tertiary carbocation. So the sort of names that we give the alcohols would be kind of reflective of the cations that would form ultimately if this sort of OH left, right? So you've seen these terms certainly in the past. And as we know, there are reactivity differences that can often take place based upon whether you can leave behind, say, for example, a primary carbocation or secondary carbocation and a tertiary carbocation. So as you might expect, that the reactivity of these could be a little bit different depending upon sort of what specifically you're trying to do. What I also want to point out here, though, is what I'm sort of not showing here, because I think that it's important early on. Much of what we're going to be discussing, right, involves functional groups, right? And And throughout this semester, we're going to see functional groups, and we're going to be discussing these different functional groups. And to date, some of the functional groups that we've seen are sort of alkenes and alkynes, and we've seen halogens. Again, the sort of name functional group implies that they could have function, right? That you could, in principle, do chemistry with these functional groups. And if you had, say, for example, this straight old hydrocarbon that just had carbon hydrogens, that wouldn't necessarily be said as having any functional groups, because all of those carbon-hydrogen bonds are relatively unreactive, and so they couldn't do anything. So when we're talking about functional groups, we're talking about specific groups within these organic molecules that could have a specific function or a specific reactivity. And the reason I want to bring this up now is that alcohols, you notice everything that I have up here is an alcohol connected to a carbon, and that carbon is connected to another couple carbons. And there are other instances where we will see OHs, but aren't necessarily considered alcohols, and I think it's worth it to just clarify this up really quickly, right? For example, sorry, methanol, you're going to go away for a second, but here's an OH that's bonded to a carbon that's bonded to a carbonyl, right? This molecule, on the surface, it sort of has that same OH as the rest of them do, but we don't call this an alcohol, right? This, reactivity-wise, is different. What would be different about this molecule than some of the others? It's more acidic, right? Because you can deprotonate that a lot easier because of the resonance, right? Again, because of these resonance, perhaps there may be differences in bond lengths and things like that we don't necessarily have to go into, but certainly I think the most obvious thing about these would be that the acidity is different. So carboxylic acids, depending upon what the R groups are, they're fairly acidic. Acetic acid, it's an acid, right? It's right there in the name. Benzoic acid, it's carboxylic acid. So this would be a carboxylic acid, not to be confused. And we'll see these a little bit more in the carbonyl chapter. And this is just one example. We'll see others, things like hydrates, for example. We'll see a lot of these more creeping up in the carbonyl chapter. But I just want to make this real quick point with the carboxylic acid. So you guys remember that alcohols, just because something has an OH doesn't necessarily make it an alcohol, right? You have to sort of think about the reactivity of it, and so this can become important. All right, so the focus of the next couple talks is largely going to be on, again, within sort of functional groups. It's going to be about how alcohols can function reactivity-wise. And we started to classify and talk about this a little bit last class, or the class before, I forget which one. One of the things that can be complicating about alcohols is that they are kind of dynamic, right? They can in fact serve as an acid, they can in fact serve as a base, right? Why? Well, they have, on the one hand, a hydrogen, right, that could in principle be extracted, but they also have lone pairs, which could in fact create new bonds, right? And so one of the reactions that we're going to see throughout, probably today, it's going to be what we sort of focus on initially, is going to involve what happens, not necessarily with the alcohol, but what happens when you take that alcohol and deprotonate it and make the alkoxide. So one class of reactions that we'll discuss within the alcohol chapter will involve taking an alcohol and treating it with, usually what I show, which we discussed last class, is sodium hydride. Right, and so we discussed this, so the product is RO minus and sodium plus. This is, I think, the best way. This is usually the way that I like to teach the generation of the alkoxides, largely because I think that we can all draw a mechanism to show this. It turns out that the cheaper way to do this, in the way that the book describes, but you're not necessarily responsible for, but you can certainly use in a synthesis problem, is if instead you treat this with sodium zero. Okay, and sodium zero will give you the same thing. If you're curious about the mechanism of this, you can talk to me afterwards, or you can look it up. But it gets to some radical chemistry that I don't want to sort of get to that much. Basically, the sodium gives up an electron, and the overall process goes through. So it's a little bit more complicated And there's other ways that we can generate sodium alkoxides to get the same product. And both of these are used. This is usually what is often used on sort of scalable, like if you wanted to generate sodium ethoxide and sell it, sodium is cheaper than sodium hydride. It's a little bit less expensive than sodium hydride. So if you're looking on a production scale, usually people use sodium. If you're doing sort of smaller synthesis, maybe you don't want those electrons around there causing problems, you might use sodium hydride. Sodium hydride is a little bit more flammable. It can react with moisture in the air. It liberates hydrogen gas fairly quickly compared to sodium, so it can potentially be a little bit more explosive. So using sodium hydride on scale isn't necessarily something that people do. But anyways, that's just so you understand some of the practical differences between these two. But I'm going to stick with sodium hydride. I would welcome you all to stick with sodium hydride as your method of deprotonating as well. But certainly other bases would deprotonate it. And how do we know if something is going to deprotonate the alcohol? Well, we have to consider, and again, we don't talk about this too much. I bring up pKa's a lot. I don't necessarily ask you guys to memorize the pKa table, but there's certain pKa's that we should get comfortable with, again, within the confines of what we already know. And so, if you're going to deprotonate an alcohol, again, an alcohol is similar to water, and we kind of discussed this last class, right? And so if we're talking about the deprotonation of water, and the deprotonation of an alcohol, they're not going to be that different. So the pKa of an alkoxide, depending upon the type of alkoxide, is going to be somewhere between, it could vary from this, but usually we're talking about 15 to maybe 17 or so, right? So again, that gets to that limit, thinking about pH, right? The high level of the pH strip is usually 14, it's what we think of, and so if you really think about what a pKa means, right, we're talking about the 50-50 point, well, why wouldn't you be able to get a pH beyond 14? Well, it's because you no longer have water, right? And so if you keep that in mind, you can remember the sort of the high end of the pKa spectra with alcohols. And so what that means is that any base that's going to be stronger or that's going to have a pKa that's higher than 15 would be enough to deprotonate that. And again, you can look at a pKa table if you really want to see that, but intuitively there's perhaps another base that you might imagine would be useful for deprotonating. It's not necessarily that you're going to want to go to, but what might be another base that you could use to deprotonate an alcohol? Let's look at the periodic table, right? You should be very comfortable. You don't have to memorize the periodic table in this class, but you should have a fairly firm grasp on about 7 of the elements and where they are. Yeah. So amides, exactly. So if you look at the periodic table, you guys are all comfortable at this point, hopefully, with the recognition that if something is more electronegative, as long as we're staying in the same row, right, the stability of these anions is going to increase as we go from left to right. Thus, conversely, it's going to decrease in stability as you go from right to left. And so nitrogen is to the left of oxygen, right? And so if you had a negatively charged nitrogen, it's not going to like that as much as the oxygen would want to be negatively charged, right? So they will switch, right? So if you were to treat this with something that is, say for example, the amide, which is NH2, and you have an equilibrium with these two, this isn't going to be happy. So the equilibrium will favor right? Does that make sense? And so again, this is just to sort of reflect on, I'm showing you a couple bases, but you sort of want to recognize that other bases might also be deprotonated. Then keep going, right? What's the left of nitrogen? Carbon. So what do you think is a stronger base than an amide? The carbon-based ones, right? So if you tried to, say, for example, run a reaction with an alkyl like an alkyl lithium, right? That's going to react rapidly with an alcohol as well. So those pKa's are even higher. So it's about, you're talking about 16 to 30 to 50, right? So the reason why this becomes important, especially when we begin to get to synthesis, and as you guys begin to build up reactions, is we'll start talking, and there'll be you guys did have a whole section last semester, right, on like Grignards, right, So if you wanted to do a reaction with a Grignard, right, do you think that an alcohol is going to survive in there? And so absolutely not. So if you try to do a Grignard reaction, we're trying to do some other chemistry, and there happened to be an alcohol around there, that's going to be a problem. So this is something that as you develop your synthetic sort of total, sort of thinking about planning synthesis skills, one of the first steps of learning synthesis is getting all the reactions together and figuring out how you can get from A to C or A to D. But that sort of next level, after you sort of get comfortable with that, then you're really going to have to start paying attention to things like functional group tolerance. And so we'll learn a little bit about how, for example, you can protect the alcohol, because obviously they're versatile. So in some cases we'll want to protect them so that maybe alcohols could survive them. But I just sort of wanted to make that point really quickly, because that becomes one of the challenges of alcohols. And we'll come back to this very, very quickly. But again, if we were to take an alcohol, and we went over this last class, if we were taking alcohol and we were treated to an acid, right? Certain acids, if they're strong enough, will also protonate this OH, right? So if we have a strong enough acid, the alcohol can serve as a base, and we can generate sort of conjugate acid that you're seeing right there. Now, I just shown a kind of a typical, just a proton that serves as our acid. But let's go back to our discussions again on pKa's. Again, I don't want you guys necessarily memorizing them, but with an alcohols, you guys should be able to know. And based upon everything that I told you, right? What do you guys think is the pKa of an alcohol on the reverse side in terms of protonating it? Yeah, it's going to be somewhere slightly less than 0, right? And so that's what it is. It's about -1 or so, right? And so what that means is that we're going to need to have something with a pKa of less than -1 to protonate a molecule like this. We were just talking about acetic acid, and again, you guys probably don't know this, but acetic acid isn't the strongest acid in the world. Again, it's vinegar, right? The pKa of acetic acid is about 5, right? So is acetic acid going to be enough to protonate an alcohol? Not enough, right? Maybe in certain reaction conditions, based upon Le Chatelier's principle, there could be a mechanism where the acetic acid protonates it. Because remember, we're talking about, I don't know my number scale, but we're talking about 10 to the 20th numbers of molecules, right, in these reactions that we're running. And so it's always possible when we're talking about an equilibrium that maybe a certain percentage of those molecules, a very small percentage of those molecules, will be protonated. And so sometimes, even if you're off a little bit, mechanisms can certainly be proposed, and reactions can be driven over time to go down these if it's energetically favorable. But in general, we certainly wouldn't think that acetic acid would react rapidly, right, with an alcohol. But what would react quickly with alcohol? What are some of the acids that we know are highly reactive with alcohols? Yeah, Chanel. Which one? Yeah, hydrochloric acid, for example. And that's a really acidic one. Again, we bring this up. If you have an aqueous solution of HCl, it's not really HCl, right? So there may be some that gets liberated from the environment because it's a gas, and so if you pop it open, maybe you'll send your nose hairs a little bit. But largely, HCl, what you have in HCl is H3O plus, Cl minus. And so in general, when we talk about like strong acids, again, this isn't a term that I generally use, but it's one that's often used. Usually what people are talking about are acids that have pKa's such that they would be protonated in an aqueous, right, environment. This is actually an interesting concept, and I had some confusion about this on my own. But Trinell just brought up HCl, right? What are some other what are some other halo acids that would also be superacids? Yeah. Yeah, Mark. What's that? HI, HCl, HBr. What about HF? No. Isn't that weird? Right? This is actually a really good, I think, lesson for something that I brought up in the past, which says that you guys can often predict pKa's based upon going from left to right or top to bottom, but you can't necessarily predict sort of diagonally. And so, fluorine is the most electrophilic atom on the periodic table, right? I forget it's like 4 something. I don't really know my electronegativity values, but it's the most electronegative, right? And yet, the counterion among the halides is not the most stable. Does anybody know what the pK of HF is? Yeah, it's something like that. Yeah, it's somewhere around 3. I'll take Mark's word for it. So, and this is actually one of the things that's bad about HF. You guys know HF is really dangerous stuff. Largely because it can actually penetrate the skin as HF, and then once it gets in, it can actually has a certain affinity for calcium in the bones and stuff like that. So it's really, really bad stuff. But it's not that acidic, and that's certainly a misconception that people often have. And so HF, just as a sort of aside, that would not react. So anyway, so sulfuric acid is in the ballpark of this as well. I think the pK of that. But you need a really strong acid to be able to sort of get to this stage. Okay? All right, so that's just a quick background on sort of the reactivity of alcohols. And what we're going to be talking about over the class today and tomorrow is really how not only we have these specific reactivities of them serving as acids and bases, but how specific functional group modifications and functional group changes can take place based upon this sort of knowledge. Okay? And so let's start with, because it's just in terms of how the flow would work best. So we'll start with the alkoxides, which is how we started this a little bit earlier. And so if we were to take an alcohol, we were treated to sodium hydride, we were able to get to our alkoxide. I'm not going to bother showing the lone pairs here, but you guys should see how many lone pairs and know how many lone pairs are here. We have effectively turned the alcohol into something that's more reactive, right? Now it can be a base, right? It can be a base. It can be a nucleophile. Again, we've seen potassium t-butoxide serve as a base in the past in terms of certain elimination reactions, and certainly we've seen alkoxides in the past serve in that capacity. They can also certainly serve as nucleophiles as well. This is where there can be a tough dynamic, right? Is this alkoxide going to make an oxygen-carbon bond, or is this alkoxide going to deprotonate something? This is one of the challenging things that sort of fall into this gray area, and the book will try to come up with specific rules that can help guide you through it. But I always think that I'd rather sort of have you guys build an intuition that would help you start thinking about it on your own. And one of the ways that we can begin thinking about how we might prevent these sort of combinations between alkoxide behaving as bases or behaving as nucleophiles within synthesis is really potentially at the beginning thinking about how we could design our system. So I thought that's what we would do here. And the reaction I want to focus on is what's sort of called a Williamson ether synthesis, right? And so this is going to be the first alcohol reaction we learned. So if we were to take R1 alcohol and we were to treat it with an R2 alcohol, sorry, not an alkyl 2 alcohol, let's say an R2 halogen, right, where that X is a bromide or a chloride, the net result is going to be this molecule that I'm showing you here. Do you know what this functional group is called? It's called an ether, right? So this is called an ether. As an aside, because sorry, just another little tidbit. So in your labs, have you guys ever used the solvent petroleum ether? This is like one of the most confusing freaking things in the world, I think. So do you guys know, anybody here, like, I think it's got its origins in Greek. Anybody here Greek? Anybody know the term? Well, you guys should know. I mean, it's a general term. If you say something's in the ether, what does that mean? Yeah, it's sort of in the air, right? And so the term ether, what are you laughing about? All right, you'll have to tell me the joke afterwards. All right, so but ether generally means in the air, and so this is sort of an interesting thing with the name of ether, and I think it's just worth sort of clarifying early on because you may see this down the road. But the term ether for organic chemists has become sort of synonymous with this sort of functional group of an oxygen connected to 2 carbons. Okay. Again, there's going to be some discrepancies based upon what those carbons are. There's things called esters, for example, that we'll get to at a certain point. within the carbonyl chapter, but when they're connected to two carbons, it's called an ether. The term ether and solvents, like diethyl ether, right? If you guys use diethyl ether in labs, right? Diethyl ether is two ethyl groups on either side. There can sometimes be some confusion because there's another solvent called petroleum ether. What is petroleum? When we think of petroleum, what are we thinking about? Yeah, we haven't really gotten to that part of the chapter yet, but you guys might know this already, that when we're talking about petroleum ether, we're talking about petro products. We're talking about things like hexanes and pentanes and octane, right? Just long hydrocarbon molecules, because that's really what oil is, and that's sort of the distillate of oil that we ultimately put into our vehicles and that we use as sort of power. And so when you hear the term petroleum ether, that's really just referring to the most volatile components of the petroleum. And it can be confusing because sometimes you guys will get petroleum ether and you'll get confused because you'll think it's a functional group ether. But that's just in case you come up with it, for example, in your labs or something like that. So petroleum ether is not an actual functional group ether. Anyway, that's just sort of a point you make. All right, so what this tells us, right, is that if we wanted to make an alcohol, if we wanted to make an ether, we can do so in a sort of unsymmetric way, non-symmetric, right? We can have an R1 at one place and we can have an R2 at the other place. And we can figure out how to do that just by having an alkoxide on one side and a halogen on the other. So let's just start to ask a question, though, really quickly. Here's a type of ether that's also solvent. This is called EBME. It's tetrabutyl methyl ether, right? And this is something that people use very commonly, particularly in industry, for solvents. But if we wanted to make this in an efficient way using a Williamson ether synthesis, right, there are two ways that we might go about doing this. And I sort of want to put them both up there, and I want to discuss which of the two you guys think might be more useful. Right? We could break bond A, right? Which would mean that or we could break bond B. So if we broke bond A, we would have this terbutyl halogen, or we could have the terbutyl ether. We would react it with bromomethane. And there's actually easier ways that this is made productivity-wise, but here's just a good example of, I think, two different ways that we could go about doing this Williamson ether synthesis. The question that I have for you guys is, if the goal is to be able to actually forge a bond, what's going to be the major byproduct that we may, as we were sort of saying earlier, what is it that we want to potentially avoid happening? The alkoxide, we want it to be a nucleophile. We do not want it to be a base, right? And how would these molecules and how would these alkoxides behave as a base in this setting? It's not like you have an acetic acid or something out here, right? But they can serve as a base through a reaction from organic chemistry 1, which is an elimination reaction, right? So looking at these two molecules, if we were to make this, what do you guys think? Yeah. So say it again. So the first reaction, you have beta hydrogens. And so what could very easily happen is you could, in fact, perform an elimination. In fact, do you think you would really get any substitution here? Probably not. Why not? Because we're kind of set up for almost like an SN1 type reaction, right? We've got a strong nucleophile potentially. And what we've left ourselves with is a tertiary halide, so we likely wouldn't be able to react on the reverse setting, right? So this is probably something that's not going to be what you'd want to do. But if you did the B, right, you're kind of in the clear a little bit more, right? butoxide isn't a great nucleophile, right? We've learned about it as being a good base that's not going to be that nucleophilic, right? But of the two options, this is infinitely better because we have completely removed the possibility, right, of doing an elimination reaction, right? Because there are no, you need a beta hydrogen, remember, to do the elimination. This methyl group doesn't have any beta hydrogens. So one of the things that you can look to do if you're doing a Williamson ether synthesis that you should all be able to identify is look at the two options, right? And one of the very early things that you could just do is ask yourselves, do one of these reactions have the possibility of doing an elimination? And does the other one? And if one of them doesn't have a potential of doing an elimination, then that's probably the one that you should choose. And if you dig deeper, there are additional rules that you can use that people have figured out, and I'm not going to necessarily go into that much depth. You can certainly read it on your own. But this is just a sort of a broader outline, but, usually people will say, what is it? Certainly avoid tertiary halides for all the reasons that we've said. Apparently secondary halides is going to be a problem as well. So again, if you read in the book, they say these things. But I tend to not want to go into that much sort of rubbish with these. But you can certainly look in there, and I think that the sort of general thought and what I want to sort of get you guys to think about is what are the two possibilities? How might one happen? How might the other happen? And try to think about what the most effective way is going to be. Okay? So this is a Williamson ether synthesis. Congratulations, we just learned the first reaction of organic chemistry. All right, so, So the other way that we can make ethers, all right, so that's one way that we can make ethers. I mentioned earlier diethyl ether. And so certainly if you have non-symmetric ethers, the best way to go about it is going to be Williamson ether synthesis, right? You have some control over this. But what if you have a symmetric ether? If you have a symmetric ether, it doesn't really matter which side of the equation is your nucleophile, which side of the equation is your electrophile. You don't have to worry about this competition. And so it turns out that one of the common ways in which case you can make ethers, and this is particularly useful if it's symmetric, is to simply do a dehydration reaction. So it turns out that if you take this molecule and you treat it with a strong enough acid, let's say H2SO4, you can in fact drive the reaction in that direction. Now I've left one thing out of this equation. Can somebody help me if we have two alcohols? Can somebody help me balance this equation? What's the difference in terms of conservation of mass on this side and on this side? Trinell. H2O, right? So if we did all our math, there's basically, we're making this bond, and we've got the hydrogen and the two OHs left over. So the mass sort of balance to this is H2O, and this is going to be an important component of this. So it turns out that if you take sulfuric acid, you take ethanol, and you react it with sulfuric acid, you're going to get the ether. Let's discuss how this mechanism might take place. And then we'll discuss a little bit about this. Okay, so if I take this reaction and I go OSO3H, based upon everything that I told you guys before, we've identified the strong acid. What's going to be the first step of this reaction? You're going to protonate, right? So we've got our set of lone pairs here. They can extract. Right? So that's going to be the first step. Now, this isn't run exclusively, and oftentimes it's catalytic sulfuric acid. We have a lot more ethanol in here. Right? So let me just put the other equivalent here just for bookkeeping. So we still have another alcohol there. So what's going to be the next step, do you think, of this reaction? Let's look at the product and think about what we might be able to do. What have we done in intuitively or in terms of strategically, is an alcohol that reactive? No. But by treating it with sulfuric acid, have we turned it into something reactive? Yes, right? Now this is a molecule that can actually serve, it can go in the reverse, right? It can get deprotonated. But another way that you can sort of, if you sort of zero in on the positive charge, right? If it was to deprotonate, you'd solve that positive charge. The other way that you could solve that positive charge, right? Let me draw this out because I think this is a worthwhile point to make. Right? What we're trying to do here, right, in the forward process, so much of chemistry, right, just make this point, so much of chemistry and mechanisms, right, is about creating a charge on the molecule and then sort of moving that charge around, right? So when you create a positive charge, it's often about fixing that positive charge or neutralizing that positive charge at the expense of the positive charge going somewhere else. Does that make sense? So when we look at this oxygen, right, and we look at the fact that the oxygen has a positive charge on it, what do we have to do to make it neutral? It's got 5 electrons to itself, right? We want to get 6 electrons. Where could those electrons come from? Can we just dump an electron into this molecule? Can we just react it with a nucleophile? No. Why can't we just have a nucleophile add its electrons to the oxygen? I know a lot of people, hopefully nobody in Organic 2 would do that, but certainly it's a common problem that people make in Organic Chemistry 1. Why can you not just attack the oxygen with a nucleophile? Why can't I do this? Why can't I do that? What's that? I'm going to violate the octet rule. I don't want to see this. I know I'm going to see it, but I don't want to see it, so don't do this, right? And the reason is we'd be violating the octet rule. So we're not going to be able to just dump electrons into the oxygen to fix that positive charge. It's already got a full valence, right? So how are we going to fix that positive charge if we can't add something else to it? Yeah. Rowan. Ramen.
So you either have the oxygen, that leaving group,
right?
It doesn't really work if it's on a primary product.
Yeah, actually, what you're 100%, everything that you're saying is correct. I want a more general statement, though. What Rami's getting to is, if we can't give it electrons, then we have to take the electrons away from the bonds that it's currently sharing, right? It's got a full valence of 8 electrons, right? So we can't just give it an extra electron. So what we have to do is we have to take some of the electrons that it's sharing and give them back to the oxygen. Does everybody see that? Right? And so when I was saying this could behave as an acid, what would I be doing? I'd be taking these 2 electrons, probably grabbing the proton and putting the electrons back into the oxygen. Same thing here would be the identical situation. What Rami was saying is, these lone pairs here we could also put on there, right? But he also pointed out that he doesn't like that. He doesn't want to just go ahead and put the electrons there right away, because Rami has learned to hate a certain kind of cation, and that is a primary cation. And so he knows that he wants to put those electrons there, but he knows that he can't just do that alone, because it would be bad. So he wants to do something else simultaneously, right? And what would that be?
Attack the lone pairs on the other.
Right. He wants to have these lone pairs here attack simultaneously. SN1 we don't like. SN2, it's not necessarily SN2 typical conditions, but it's the only way that we can do it without upsetting Rami with the primary carbocation and upsetting me. I don't want to see that either. All right, so now we've got this plus water, right? And again, I mentioned this is catalytic with sulfuric acid. So how do we make that oxygen, going back to the same thing we were talking about before, how do we take that oxygen that's positively charged and make it happy? Well, again, we can't add a nucleophile to it. So let's look at the electrons that it's sharing with things. If I grab those electrons, where would I be going? I'd be just going in the reverse. Same thing, this, it's symmetric, I'd be going in the reverse. The only way forward is these protons right? And however we do this, there's multiple things, and in truth, it would probably be the ethanol doing it, but I usually like to use the conjugate acid. In this case, we have the conjugate acid, I misspoke, the conjugate base, the sulfonate, as our base. And this way we will get to, right, ultimately our product, and regenerate the sulfuric in the process. Yes?
I did this in the previous sentence with ethanol. First ethanol. Instead of.
So take me through it.
So making the.
So great. I'm really glad you asked that question. What's your name?
Yeah.
So Dan was just asking a question. He wants to have this sulfonate deprotonate that alcohol. And this is something that I see a lot. 10-point question, how to lose a point. Why would I take a point off of Dan's critical final exam that he needs every point possible? Why would I take that point off? Because we're way off on the pKa spectrum there, right? Like this, again, a pKa of sulfuric acid, this is a really strong acid. We're talking about -2. This, to deprotonate this, would be up around 16, right? So you see what I'm saying? So it probably you want to wait and hold off. And this is actually another way to sort of think about this is, people often bring up and this is not a hard rule that you want to stick to, but it can be a rule that can help you. Oftentimes, you want to try to avoid making in your sequence, usually that first step, okay, you're leaving behind that negative charge. But at that point, you kind of want to avoid the unreactive components having positive and negative charges. You kind of want to avoid, unnecessarily having to create a charge somewhere that you don't really need to. So that would get you there from the standpoint of bookkeeping. And that would be, I would say, a B answer. But the A answer is to make sure that you're also keeping in mind some of those charges. Okay? All right, so the other thing, and we sort of pointed this out as we were going through it, and we were looking at how we fix all these positive charges, is you notice that as I was going through this reaction, every single time that we went through it, I said, sort of pointed to the fact that these other electrons could go, and that would lead us in the reverse direction, right? If you don't believe me, go back and watch the video, because I did say that. Which basically means that every single one of these reactions is reversible. And I would urge you all, I'm not going to go through it, give it time, but I would urge all of you guys to try that. So I showed you how to take ethanol and convert it into diethyl ether. I want you to, on your own time, convince yourself that if you took diethyl ether and water, you'd go in the reverse direction. And it's quite literally the exact same reaction from a mechanism standpoint. Okay, and so try to work that on your own. But that raises a question. If you can go in both directions, how does it work, right? How do we have a system where we have all these reversible reactions, and how do we get it to go in one direction rather than the other direction? Ron?
In regard to pKa's.
Well, so no, there's no pKa in here. I mean, alcohol and diethyl ether are virtually. The pKa is a little bit higher with the well, actually on the lower end, I don't know how it differs, but they're ballpark the same. It's not a pKa, that wouldn't work. And if that were to work, then we'd have no control. It would only go one direction, right? So there's got to be something that we can do here to actually be able to control it.
Remove products.
What's that?
Remove products.
So yeah, so what are you getting at? Let me just erase all the noise. Let me just erase all the noise and get the important stuff. So what I just said, right, is that this plus water with a little bit of acid can basically take you in one direction, and can also take you in the opposite direction. So remind me again? Shayna. Shayna, yes. I know your names. I just have to be reminded occasionally. So Shayna's saying she wants to remove something. What do you want to remove?
So we're trying to get to the diet.
So if we want to go from here to diethyl ether, for example, what would we do?
We want to take the diethyl ether away.
Okay, so one option would be to remove the diethyl ether from the equation. And how might we do that? That could be an option. That wasn't where I was going, but you could do it. I want you guys to think about how you might do that. How might we remove diethyl ether from the solution? What's that?
You start off with pure ethanol.
So we started with pure ethanol, and we added some sulfuric acid. What would happen is we start generating diethyl ether and water, and maybe there would be an equilibrium where we have 50% of one and 50% of the other after a certain amount of time. But if we want to push it all the way in a specific direction, Shayna's intuition is spot on. She wants to, well, hold on, so she wants to remove the diethyl ether, and what is she invoking? What basic principle of sort of Le Chatelier's principle, right? By putting pressure, by removing the diethyl ether from this side of the equation, we can push the equation in this direction, right? But how do we remove diethyl ether? She brought up, is the diethyl ether and water maybe not miscible in one another? It's not a bad thought, right? If they're not really coming in contact, maybe you could push it in this direction just based upon the properties of the two molecules, not necessarily mixing as well. I wasn't thinking that, but it's a good thought. Mark? What's that? So they're both, okay, maybe go on, keep going. Yeah. Well, but if you just mix these two, you get equilibrium regardless. So from a heat perspective, you've reached thermodynamic equilibrium. The question is, how do you push it in that direction? What's that? It doesn't matter. It's both. It's the same energy in both ways. It's going to reach a global equilibrium, roughly. Yeah?
I think to add a strong acid to diethyl ether, you would swing the one phase on the oxygen.
Because it's going to be the same reaction in reverse. The point here is maybe we're missing some information that would help us figure this out. So let's take a step back. Ronnie, hold that thought for a second. But let's ask ourselves about some of the properties. Shayna brought up a really good one property. She said, well, ethanol and ethanol, they're going to be mixed because they're the same. Ethanol and water, maybe they're not going to mix that well, and so maybe you could drive it just based upon the fact that the two won't mix. What's that? That's what Shayna was saying. Yeah. So she's saying these aren't going to be soluble, so they can separate. And that's a good thought, right? If they're not going to be able to mix, maybe you can draw it in that direction. But for that same reason, why did she say that these aren't soluble in one another? Yeah. This one's polar, this one's nonpolar, relatively, right? So they're not going to be miscible. What else does polarity and nonpolarity do to molecules oftentimes, aside from making them not miscible with one another? Boiling points. So the boiling points, and you'd have to look this up, and we don't necessarily have the information on hand, but I know the rough numbers, right? But water, we all know what the boiling point of water is, right? It's 100 degrees Celsius. Diethyl ether, does anybody know what the boiling point of diethyl ether is? Yeah, it's in the 30s. It's in the mid-30s, so it's pretty volatile. And then on the flip side, ethanol is somewhere in the 60s, 70s, 60, 70 range. So one thing that you might be able to do is boil off, maybe have a distillate at the other side that's sort of pulling the diethyl ether out by distilling it into somewhere where it's doesn't have water or acid, right? So maybe you could distill it. So that's a good idea, and certainly you can do that. But what if you're not dealing with something where you could take advantage of that? What if we're in a special situation here where we had diethyl ether, but what if we had a bigger alcohol that we couldn't necessarily distill one, and there's no changes in them? Well, in this case, we got to resort back to the water. And the thing about the water, and this isn't necessarily, I'll just sort of keep moving forward because this isn't something that I think you guys would inherently know, but water is, well, you guys do know water is special. But one of the things about water is that water, for the reasons that Shayna was bringing up in terms of non-miscibility, we'll get to that in a second. There's something called a Dean-Stark apparatus that will take advantage of that in kind of a controlled way. But the simplest way that people will do it is there's a lot of materials, specifically things called molecular sieves, for example. Do you guys ever work with molecular sieves? They're these like metal, it's like titanium, and all these, I don't know, it's like this ground up stuff that has pore sizes that are just big enough that they basically become a sponge for specific size molecules. And there's ones that are specifically geared towards water, and they can actually pull the water out of the solution. So one thing is molecular sieves, right? And again, these are porous materials that effectively serve as sponges to suck the water out of the reaction. The other thing is, again, is kind of, and I'll show the picture of it, is something called a Dean-Stark apparatus. And there's different types of Dean-Starks, but it sort of gets on the principles that we were kind of learning, right? Usually when we have a reaction running, right, there's some, you're maybe boiling the reaction, and see, down. What you end up having is this. Sorry, it's not the best artistic thing, but I'll try to explain what's going on here. So what we have is we have a reaction flask, and then there's usually this sort of curved, you guys have seen these in your lab drawers, the sort of curved connector things that are two-way at this point. One of them goes to a second flask, and then at the top you generally have, you should probably tell based upon this fantastic drawing of one, is a reflux condenser, right? So what's going to happen is you're going to have your mixture here, right? And it's going to boil up, similar to what we talked about before. But the problem, the challenge with the boiling off, as we were discussing before, is that it's rare that you're going to be able to boil off the ether without taking some of the water with it, right? That's going to be some of the challenges with this, right? It's not, when things are boiling, it's not necessarily about this boiling and that not boiling. Usually they boil as some percentage of the two, and it's never going to be 100% of one and 0 of the other. And you guys have done probably experiments of this in Organic Chemistry 1 where you show it, right? Where you've tried to do distillations and you'll see a specific boiling point that'll tell you sort of how something is, and you'll go through these sort of points in that distillation where you'll have a boiling point that'll be in between the two, and it's because what you're actually distilling over is a mixture, right? So for those reasons, boiling away the diethyl ether might not necessarily be that, but you could boil over the two in combination. And then what generally happens is you have enough, say for example, solvent, because usually you have a solvent here, so what you're going to do is you're going to boil not only the two reagents that we said, but you're also going to have the solvent in there. And the solvent and the water, and usually that's it, because oftentimes the product that we're generating is so heavy that it doesn't come off, right? So this is more practical in big molecule synthesis. But what ends up happening is the water will go up with the solvent, they will distill, they will come back down, and then they will separate. And because the water is heavier than most organic solvents, not all, but most, the water will sink to the bottom, there'll be volume displacement, and you'll replenish the solvent, right? So you don't dry out your reaction flask. And so this is another way, it's called a Dean-Stark apparatus. And there's a little fancier one that's sort of flip-flopped. Say, for example, if you're using dichloromethane or something that's heavier than the water, there's another way to do it. But the whole idea is you're basically boiling off the solvent and the water. Usually this is done with heavier molecules where the molecule isn't going to, the molecule's going to stay here. But you don't want to dry out your reaction. So this way you're able to drive off the water and replenish it. So take-home point is there are ways to drive a reaction by removing water from the reaction. The reverse solution is a little bit easier. If we want this to go in this direction, how would we do that? Add water, right? Don't get much cheaper than water, at least not yet. But at least we can use water in excess, and we can sort of drive the equilibrium in that direction. Okay. So this is chemistry that's largely, and we'll talk about a few other reactions like this, but this is kind of what we would often call a dehydration reaction. Okay. So this is just an alternative way that you can make ethers that I think drills home the point that we can sort of push in one direction or another. All right. Moving on. So we did this, we did this, we did this, we did this, we did this. Okay, so let's see what we got here. Great. Okay, so another dehydration reaction. How many we got? We got 20 minutes. So another reaction that we classify as a dehydration reaction. Nobody's picking up the irony of dehydration. talking about dehydration in this classroom. We talked about this last class, that another dehydration reaction, we actually went through this exact reaction last time, right? Another dehydration reaction would be one where you take an alcohol and you treat it with an acid, right? And specifically what we're talking about is an acid halo, like HBr, HCl. Again, this isn't going to work with HF, but certainly HCl, HBr, HI. Right? The product of this reaction is ultimately going to be an alkyl halide, right? The byproduct of this reaction is what? Water, right? Same thing. Right? So the byproduct of this reaction is water. And based upon the sake of time, I'm not going to go through this mechanism. We did it last time. I hope you guys could all do this. You can make the alcohol, depending upon the nature of the R group, it'll leave, and you'll get something back there. But I want to make a point about the fact that in general, this will often proceed through a carbocation intermediate. And this becomes important for a number of reasons. First of all, alkyl halides are going to be some of the most versatile groups that we've seen, right? We saw this in Organic Chemistry 1, like the go-to electrophile to make carbon-carbon bonds was often, right, a carbon-halogen bond, right? Halogens are good leaving groups. You want to attack the carbon, leave the halogen, so that's pretty much kind of our go-to. So if we want that carbon-forming nucleophile, or sorry, excuse me, electrophile, it's going to be generally a halo, halo alkene, right? We also saw last class that what's another really versatile thing that we can do with alkyl halides? We can also, just like alcohols, we can also convert alkyl halides into nucleophiles. How do we do that? Talked about it a little bit earlier. Did I hear it? Somebody? Oh, maybe it was somebody out in the hall? Yeah. So if you want to take an alkyl halide, and we want to turn this into something that would behave as an alkyl anion. Mark. So we could do magnesium, right? What would that be called? If we treat an alkyl halide to magnesium, we just talked about that earlier. Grignard, right? So if we treat that to magnesium, it becomes the sort of the magnesium bromide, for example, counterion. We could treat it with lithium, right? We saw this, which then can be converted to the Gilman. So the point that I'm trying to make here is this is going to be the conversion of an alcohol, especially in some of the synthesis problems that you guys are going to be doing. The conversion of an alcohol into a halide is going to be very important because halides, we should already recognize, are very versatile themselves, right? Halides can be electrophiles, and not just electrophiles, but this is organic chemistry, and we're talking about carbon-containing molecules, and so making carbon-carbon bonds is important. So what we're talking about is a carbon-based electrophile that you could potentially make a carbon-carbon bond with. At the same time, we can turn that into a carbon-based nucleophile, which we can also. So again, that's, I don't want to understate the importance of halogens within that extent. But the potential problem with this reaction that we've seen here is something else that can sometimes happen, right? And again, it's difficult to predict these sorts of things sometimes with let's say, for example, I don't know, let's say this, right? Let's say, for example, that we want to take this and treat it into HX, right? So here we have a more complex halogen, right? And we want to take this molecule and we want to treat it with this compound here. Again, the first step is going to be protonation. Under the conditions here, what do you think is going to happen next? We're going to generate the carbocation. And then what's the potential problem with carbocations? And I set this one up specifically because it's one that could have this issue, right? Carbocations are high energy species. You can begin, when you have carbocations, you can begin to do elimination, or sorry, rearrangements. You can begin to do sort of bond and sort of reorganizations, right? And in this case, we have a secondary carbocation, and I purposely set this up to show a potential problem. maybe it's a benefit. Maybe you want this to happen, but if you simply want to convert that molecule, what can happen is you will eventually get this equilibrium that will largely favor the formation of the tertiary carbocation. You guys remember this? Sort of carbocation rearrangements. Okay? And so the product, while you might want to get the product where the carbon forms there, you might end up getting a different product, right? You may end up getting the product where the bromine now ends up not on the carbon that you wanted it to be on, but it ends up on a rearranged product that could look like this. And again, maybe that's something you want to do, and maybe that's something you can use strategically. But it also reveals a potential problem if it's something that you don't want to do this with. So in general, we usually don't use HBr, HCl, HI as means to go about making carbon-halogen bonds. What we do is we have some reagents that are much more efficient and that don't necessarily go through these same issues. Okay, so again, there's a few little funky things about these mechanisms, and so depending upon where you read about the mechanisms, sometimes you'll see some interesting, like, sigma migration processes, but I'm just going to try to keep it simple based upon what you know. So if you see a mechanism in the literature that looks a little bit different than what I show, that's probably right. I'm just trying to simplify it for you guys to help sort of make sense of it. But there's a couple different ways in which, let's start with chlorides. So the ways in which case we can go about making chlorides, and usually the reagent that we use is SOCl2, right? Is this molecule here. And as I stated last class, one of the things that I would encourage you guys to do is look through the reactions, and you guys have never seen SOCl2 in your lives. Well, maybe you have. Most of you probably haven't. And this is the first time that you're being introduced to this new reagent, but yet you look at the reaction and you find that the product of this reaction is an alkyl chloride. And maybe what you also find in this reaction, you start looking at the things that are going to be forming here, is you end up with sort of HCl, and you also end up with SO2. Okay? And what this becomes is a good opportunity to try a semi-challenging mechanism question, right? To say, can I figure out a reaction that could actually lead to these products? And I think there's a few different ways in which case you guys could go about showing a mechanism here that I would be pretty happy seeing. But let's talk about it a little bit. All right, so what would we do if we were looking at this reaction? So again, one of the first things that you might do is try to identify the nucleophile, try to identify the electrophile. In this case, that might be a little bit challenging, right? Because we've never seen SOCl2 before. Is SOCl2 going to be an electrophile? Is SO2 going to be a nucleophile? And so it's not as obvious necessarily as sulfuric acid. And that's why I would say I wouldn't be too tough on yourselves if you chose wrong here in terms of what the reactivity is. But what do we think? What do we want SOCl2 to be? We want it to be, how might it be an electrophile? Let's just start off with. It could potentially be an electrophile if we attacked, well, we haven't really discussed carbonyls yet, so this becomes very difficult. I'm going to draw this different. I'm going to draw, just to keep things safe, I'm going to draw this tautomer, which is actually sometimes how it looks. So let's draw that. That'll make our lives a little bit easier so we don't have to jump ahead to the carbonyl chapter. I've redrawn SOCl2 in what is just a resonance form, right? This is simply, I just push the electrons in the double bond up into the oxygen to help simplify what we're looking at here. So can this behave as an electrophile? Lewis acid? Absolutely. We could potentially attack that sulfur, right? Where it has a positive charge. Again, we just moved electrons away from it up to the oxygen. Could it serve as a nucleophile, or could it serve as a base? Absolutely, right? There's an oxygen that has a negative charge on it, and that could serve as a base as well. So at the beginning of a reaction that you would see like this, I think especially at this point in the game, either one of those that you did, if you chose to take the SOCl2 and you made it a base, or you chose to you chose to make an electrophile, I think that's okay, and I think that's healthy, and I think that's, like, part of the process. And truthfully, you can get the correct answer ultimately either way. So let's just start by picking one. What do you guys like better? And give me some reasons why you might want to pick one rather than the other. What's that? So you want to use oxygen as the base, or this is the base. Okay, so if this is going to be our base, what's going to be our acid? So if this is our base, what here is going to be our acid? Right, the hydrogen, right? So if we were to actually do this, the first step of this reaction would be something like this. When we make that bond, we get to an intermediate like this. Again, I'm not saying this is the mechanism, I'm just saying that you guys can convince yourselves how this product could form, and it would be reasonable, especially at this phase of the game, right? You don't really know anything about SOCl2 yet, so whether SOCl2 serves initially as an electrophile or a nucleophile, you might not necessarily have the knowledge yet to be able to predict which one would be. All right, so now we've generated a nucleophile, now we've generated an electrophile. What might we be able to do here? Probably just attack the two. That's a pretty easy one, right? We've got a negatively charged oxygen here. We've got a positively charged sulfur there. We get to a molecule that looks something like this. Now at this point, the mechanism may get to a point where it might be a little bit challenging. So maybe we should take a look at the product and start to think about, in that product, what ultimately do we want to do? And I'll point out that whether or not you use this as an acid or whether or not you use this as a base, my guess is you probably get to that same intermediate ultimately anyway. So now you've gotten a little bit of a more challenging part to it, which is here's something kind of interesting. We've got, this sort of pentacoordinated sulfur. Let's look at what we need to make. We need to sort of get a carbon-chlorine bond at some point, right? We at some point need to make sort of double bonds with the sulfur and the oxygen. And so we probably, it might give us some hints on some of the things that we might want to do here. Does anybody have any thoughts? Aisha? So Aisha wants to have one of the chlorines leave. All right, so let's take a look at that and ask if Aisha's crazy or if she's onto something here. All right, so Aisha wants to have the chlorine leave. All right, let's take a look at that. So I just pushed the arrows to have the chlorine leave. Do we like this? I'm saying it in a way that's trying to tell you guys that you shouldn't, but in fact, I'm tricking you. Or maybe I'm just tired. But why? I kind of like that. What is it that I like about the chlorine leaving there? Yeah, Rami.
That hydroxyl group make a resonance.
Yeah, I mean this is fairly stabilized at that point, right? That sulfur, that cation, this goes back to conjugation. That sulfur has a resonance form. So if I want to use detailed and show resonance arrows there, really what we have here is that molecule there. What am I missing? I'm missing a positive charge, right? All right. All right, so now we've got this intermediate. We've got a chloride. So kind of like that. Aisha, why did you think about this? What made you think of this? Because you're looking at the products, and you wanted the chloride to be, what was your intuition that you didn't? You did, yeah, right. So you saw that sulfur looks a little bit stable because I recognize it can be stable through resonance. But I also like the fact that now I have a chloride. And why do you like the fact that you now have a chloride? Well, chloride's kind of stable, but looking at the product, what else could the chloride help us with here? Well, it could take a proton from the oxygen. That would regenerate HCl. We could do that. This is where the true mechanism of this actually becomes a little bit challenging, because it involves this bizarre like sort of ortho elimination. Like I don't usually teach it that way because I think it's a little bit more complicated. But what else is chloride? So chloride being an acid. What else could the chloride be? Sorry, I just included this book. The chloride could be a base and abstract, but it's not a very good base. It could be a nucleophile, right? And if this is going to be a nucleophile, where could the chloride attack? If I attack that R, we're going to be pushing a few arrows here, but let's take a look. If I were to attack that, yeah. We got to move these somewhere, right? They can't stick, otherwise we have too many carbons there. So when we attack, those that have to move, they can really only move one place. Well, they can move onto the oxygen, but if they moved here. So we've got a couple options here. We can kick out the Cl, which is what you want to do, or you can kick the OH up onto the positive. Now, based upon what I was saying earlier, usually you're trying to fix that positive charge, so I might say you sort of jumped ahead to actually where we would be going, and everything you just said could be possible there. But given the fact that we're often trying to fix that positive charge, I'm going to push the oxygens up onto that. That oxygen. I'm starting to run out of space here. But what I've done is I've made my alkyl chloride. Oops, sorry. So I have that intermediate there. And from that intermediate, if we just look at the product, we got to generate H2O and HCl. So maybe what we want to do is push these electrons back down here, which is initially where you were going anyway. That's going to make SO2H, Cl minus, and that's going to then abstract it, ultimately get the product. Now again, we sort of went through this mechanism together. If you look in the book, or if you look online, there are some subtleties that aren't quite exactly what we have here. And a lot of these have been studied with details and sort of, tracking where oxygens end up in different points. And so this mechanism is not entirely accurate. But did it get us there? And not only that, did it get us there without anything overly crazy, right? There's nothing about this mechanism. We're not breaking any octet rules. We're not, the only real thing that this does, that the real mechanism helps explain a little bit better, is why sometimes we won't get rearrangement products, right? Because it turns out that there's a sort of, again, you can look online. I don't teach this usually because it's a little bit more complex. But the point that I'm trying to make here is that you can rationalize this based on everything that we know. Yeah?
Yeah, quick question. How do you know in the laboratory at least that you want that chloride to attack specifically the carbon that's attached to the oxygen? Before we know there's a carbon chain of 4 or 5 carbons, how do I know that chloride's going to attack that carbon that's next to the oxygen?
How do we know that chloride? So that oxygen is going to be fairly electrophilic. That this sort of leaving group is a little bit less. Usually, what I sort of tell to sort of at least rationalize it is this is a good electrophile and doesn't necessarily need the full positive charge. That's kind of baloney, but it's just a way to think about it. But I'm not quite sure. So chloride is not a very nucleophilic group. Chlorides aren't going to go and start attacking, random parts. Certainly this chloride, it could abstract the proton here, and we could probably still get to the mechanism there at some point by breaking it down. So again, there are other mechanisms that can get us there. What you're asking, though, is more about sort of the overall reactivity, not just the mechanism, if I'm understanding right. You're asking a more global question. And without seeing a specific example, it would be a little bit difficult, to sort of understand that. So, all right, so I just want to make a couple points. So again, do not hold me to this mechanism. It's not the exact mechanism. You can find more details on the specific of this mechanism. The point was that we sort of went through it together, and we were able to rationalize the way through it. And if you showed me this mechanism on an exam, I would be happy with it. Try to do a similar mechanism with BBr3, which is how we go through how we make bromides. I may not have enough time to go. We may have to just fly through it next class, but that's where we'll start. And continue on the alcohol chapter because we're going to try to get through all the remaining alcohol reactions next class. Okay? All right.